Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Mohamad Falich, and I would like to present a research about an optimum design and economic analysis of renewable PV standalone power plant for electric vehicle charging station in Indonesia. First of all, why we should build a charging station in Indonesia. Based on International Energy Agency or IEA, 1.97 million electric cars were sold worldwide throughout 2018. This data increased by 68% compared to 2017. Indonesia has begun to show its seriousness in this matter by issuing presidential decree about battery-based electric vehicles. In Indonesia, it's assumed that electric cars would start to be used in 2025, with the number of electric cars is about 20,000 units, and increase to 36.5 million units of electric cars in 2050. If this is achieved, the total fuel savings in 2050 for gasoline would be 2.19 million kiloliter. Meanwhile, electricity demand would be increased from 36.9 gigawatt hour in 2025 to 46 0.3 terawatt-hour in 2050. One of the main components in supporting electric vehicles is the availability of a charging station. With the use of battery electric cars, it is necessary to develop about 1,000 fast charging stations in Indonesia. Therefore, we should utilize renewable energy potential like PV to provide electrical energy because of its cheap and long-term capability. The study outlines an economic analysis feasibility of PV in Semarang city. The location has a good level of solar radiation. The site under consideration represents fairly dense settlements with lots of water near sea, which is good for PV cooling. The scope of this work is an electric vehicle charging station that could produce electricity for 10 electric vehicles with a battery capacity of 8.8 kilowatt hour each every day. So the total daily load approximately 88 kilowatt hour. In this study, Homer is used to design the system under consideration shown in figure below. Schematic diagram consists of PV array, battery, converter, and EVCS as a load. System component description 3.1 Photovoltaic array with solar irradiance data. A solar irradiance data per year is defined by the daily radiation for horizontal PV array measured in kilowatt hour per meter square, and these data are collected from NASA website. In this study, a Paymar SG290 MFV flat plate was used, with table below as a parameter for specification is shown. The PV array power rating is 290 watt, power efficiency 17.8%. 3.2 Converter. The proposed system power plant needed to be integrated with an AC-DC converter to facilitate the EVCS. The characteristics of a converter are its inversion and rectification efficiencies, which are assumed 95%. 3.3 Battery. Batteries store the electricity generated by PV in off-peak periods, when the demand for power is usually low and fed back into the system during peak periods or when PV is not generating enough energy. But battery also reduces the fluctuation effect associated with renewable energy resources because of its stochastic characteristic. 3.4 Electric Vehicle Charging Station. EV charging station or charging point for electric vehicles is an element in the infrastructure that supplies electrical energy to recharge the batteries of electric vehicles such as electric cars or hybrid cars. The component of the charging station shown in this figure. EVCL will use both RV level 2 EV charger 240 volt 16 ampere and SAE G1772 2010 standard as a port, charger, and connector. Methodology in designing and optimizing renewable power plant by combining elements of power plants, that is PV, battery, and converter, then calculating economic analysis. 4.1 Net present cost. The NPC indicates the installation cost and operating cost over the lifetime of the system, including all the components minus salvage. 4.2 Total annualized cost. TAC is the annualized cost of each component and equipment of the system, including capital, operating, maintenance, replacement, and fuel costs. Cost of energy. Cost of energy is the average cost per kilowatt hour of the use of electrical energy produced by the system. Results and discussion. We investigate the economic analysis of the proposed PV standalone system based on the component specifications, cost, meteorological data, and electrical datasets. The simulations were carried out each yearly hour. Few cases were examined to find the optimal system configuration. NPC is taken as the cost of a system during 25 years of the whole project lifetime. The most reliable and cost-effective configuration from the proposed PV standalone system is 23.2 kW PV, 40 kWh battery, and 9 kW converter. Figure below shows the cash flow of the proposed system by components during the project year. The initial cost of the system was found to be 714 million. There is a replacement cost of 168 million in the 15th year of the project to replace the battery and converter, as well as a salvage cost of 35 million at the end of the project. The total net present cost from the system was found to be 848 million. The cost of energy estimated to be 2,300 per kilowatt hour, and the annual cost or TAC reached 65 million. The total NPC system consists of 472 million or 37% for the cost of PV array, 320 million or 55% for the cost of battery, and 54 million or 6% for the converter. All that includes the replacement and operation costs. The yearly mean power generated by PV standalone system is given in figure below. The annual project of electricity generated by the system has a total 36,000 per kilowatt hour per year, with all of that produced by PV array. The PV standalone power system successfully fulfills the unscheduled load demand by 32,000 per year. Besides, the dumped energy was about 4,700 kilowatt-hour per year because of there is no schedule for production and demand. The conclusion is the purpose of this paper is to design and analyze modeling technique which implements renewable energy source like PV to design a power plant for EVCS. The total NPC system consists of 37% for the cost of PV array, 55% for the cost of battery, and 6% for the converter. The most recommended choice with its cost effectiveness and expected to spread across the country of Indonesia in near future. This is the references of the paper. Thank you.